Next, we're going to talk about Chapter 5, calculations for sterile compounding. So we've already done the pre-course assessment review where we've gone over calculations and the different primary types of doing calculations, whether it be ratio proportion, dimensional analysis. So this chapter is going to review those concepts as well. The beginning of the chapter with historical content talks about the origin of measurement, early systems of pharmaceutical measurement, including the apothecary system, the avoirdupois system, the household measure, and what we use today is primarily the metric measure. Also talks about some inconsistent methods of calculations, including pediatric calculations, Clark's rule, Freed's rule, Cowling's rule, and Young's rule. There is a comparison on table 5.1 of the different 4 children's dosing rules. We will review those because they do still turn up on the certification exam. So, calculation, regulation of standardization in practice is important. It helps to reduce error, and we really are trying to get away from those conversions of especially the apothecary system of measure. So in this chapter, the objectives are primarily to practice several different types of pharmaceutical calculations and determine the best method for solving the problem. Now, although the book is going to have you identify, in this circumstance, which is the best method, it's generally been my practice with students to tell them, find the system that works for you and stick with it. Apply it in all circumstances. And most of the ways that Miss Ashante and myself will teach you are something that will work in every situation, instead of trying to say, well, for this, I use this, but if I'm doing something different, I use something different. Stick with one, and it'll serve you well. So, the majority of the compounded sterile products will require calculations. So we saw the label in the previous chapter with gentamicin ordered. Well, it just told us how much gentamicin it wanted in the bag. It didn't tell us how much of our stock solution would give us that gentamicin. So we will have to do that calculation. We want to use logic in approaching math. So the ratio, proportion, and dimensional analysis help to do that. So looking at the protocols, calculations are done in the anteroom. We don't do them in the clean room because we don't bring paper in, we don't bring pens in generally, we don't bring calculators in, so we're going to do this ahead of time. Also, when we do that, then we'll know what do we need to complete our order. So it's kind of like a recipe where we have to determine how much of the additive to put in there. So the prescriber tells us that what they desire for the medication, generally what the base solution is, as I referenced in Chapter 4, that may be something that's in the pre-existing order set in the computer system, or something we have to go and look up if it's not specifically ordered. The desired amount, or the dose the physician wants, the interval, so is it given once a day, is it given every 24 hours, twice a day, every 12 hours, every 4 hours, and things such as that. The prescriber also determines the infusion rate for large volume parenteral, but note that most small volume parenterals are just administered over a standard amount of time, like infuse over 15 minutes type of thing. Once the medication order is received, we enter it into the information into the computer system, and we generate the label, and then we go back and we verify it against the original order. So I referenced that at the end of Chapter 4. We want to make sure that the information matches 100%. So you can also review in this chapter the common terminology and abbreviations that we use, milligrams, milliequivalents, micrograms, and such. So the calculations themselves, they're based on the information on the compounded sterile product label and by using the stock medication container. So we begin the calculation process by determining the concentration or the dosage strength of our stock solution. So here we have a stock solution of ceftriaxone. So what we would look at on this order, let's see, get our little pen here and take our highlighter. All right, so in this case, we've got 1 gram of drug, and we're going to use, we've got a single dose vial, but we need to look at what will be our concentration. So we have to read. So this is sterile, non-pyrogenic, preservative-free. Each vial contains 1 gram. Reconstitute with sterile water. Shake well for concentration of ceftriaxone. We're going to dilute with 10 with a final concentration of 100 milligrams per milliliter. So if the doctor had ordered 1 gram, we would drop the entire content of this vial. But we'll say that the order was for 750 milligrams. So then we would have to do a calculation. So we always start with what we know. We've got 100 milligrams per milliliter, and I need 750 milligrams. So how much will I need? So I've used ratio of proportion to set this problem up. So we'll talk more about how to solve these types of things in the upcoming slides. All right, so one concentration is that the volume in milliliters or liters in the strength, and if it's in a percent strength of the base. Those solutions are not included in our calculation. A base solution is not part of our calculation. That's just the carrier vehicle. So we need to know how much we're going to put into that. Now, sometimes we will need to determine how long the bag's going to last or how many bags we might need if we're doing an IV run. We want to cut down on waste, or we need to know when do we need to get the next bag to the nurse type of thing. We also may need to calculate drop rates or flow rates. Some special considerations, like I said, the base solution, but another consideration is calculations that an IV technician chooses the method or the formula based on the type of the CSP being prepared. Mostly it's going to be your personal preference, but we're going to go through the different 3 primary types of calculations. Before we do that, I want to talk about something we call the 10% rule. So in general, we don't usually worry about how much fluid we're going to put into an IV bag. If a doctor wants an antibiotic, most of them, we're just going to put the amount into the bag, and we're not going to think about the final concentration of the bag. However, in certain circumstances, that concentration is very, very important. It has to do with the stability as well as the administration of the medication. So especially with chemotherapies and TPNs, and on some occasions antibiotics, the CSPs required the technician to pay special attention to the total volume, and that should say final, concentration of the finished product because of stability of the admixture or dosing that's based on the concentration. So if we don't have the proper mix and we're dosing it based on what we perceive that mix to be, the patient could be underdosed or overdosed, generally underdosed. So the 10% rule is used if the amount of drug added to a base solution is greater than 10% of the bag's content. So what does that mean? That means if we need to inject 15 milliliters of a solution into a 100 milliliter bag, next one. That's going to be 15%. So what we would do is we would withdraw 15 milliliters from our solution prior to injecting the drug into the bag. So, like I said, if we're going to add 15 milliliters, or in this case, we'll say the order was for 300 micrograms, into a 50 milliliter bag, we need to take that out. Because if we put 15 over 50, that's actually 30%. So we're way, way out of concentration range. Now, this is important because in this case, if it's mixed properly, we have 300 micrograms in 50 milliliters, which gives us a dose of 6 micrograms per milliliter. So if the patient was supposed to receive 1 microgram per minute, we would be able to convert the minutes to milliliters. If the 15 milliliters was not removed, the concentration would end up being 300 micrograms in 65 milliliters. So that would give us a concentration of 4.6 micrograms. So that could have an effect on the dose base if we're giving it according to micrograms per minute. In addition to understanding basic math principles, the technician must memorize common equivalents or metric conversions. So your textbook has several charts, and most of these you learned in math and practice in 106, in 102 and 106 as well. So like 1 teaspoon's 5 milliliters, 30 milliliters is 1 ounce, and so on and so forth. 1 liter is 1,000 milliliters. Also important is your standard and military time conversions. We document using our international or military time. All right. For dosage calculations, begin the calculation process by determining what? We're going to need the concentration of the drug that we're beginning with, or the dosage strength. All right. Standard time is called what? That would be clock time. So if you look at the clock, and right now it is 8:47 a.m. That would be standard time or clock time. All right. Continuing on to review the different types of formulas. So I don't like to teach formulas. Ms. Shante and I shy away from teaching formulas. The book addresses it. There may be questions regarding it either on your test or in your quiz, so I'll address it. So there is a formula. So this is primarily when they order a single medication. It's in an injectable form, and most often it's easiest when you're using 1 milliliter dose. The basic formula is D over H equals X. So D is the desired dose. H is the concentration we have on hand. And it's implied that it's over 1. So that's why we don't have any additional information. So using this, finding the desired dose, D, we would have to be given by the physician. Determine the concentration on hand. So in this case, that would be our 40, and it's over 1 milliliter. So it would be whatever the order is divided by the 40 gives us our answer. So, for example, if the order is for 120 milligrams. Our desire is 120. What we have, that should say 40. So that should be 3 milligrams. I have no idea where that 30 came from. So anyways, doing it properly, 120 divided by 40 is equal to 3 milliliters. This formula just forgets the units until the end. So again, use this one with caution. We want to use units because that helps us make sure that we're not making an error. Now, the other piece of this basic formula is what we call the D over H times Q formula. And then this is when the volume is something other than 1 milliliter. In both these formulas, D is a desired dose and H is on hand. In this one, Q is the volume, the concentration of the drug is. So we don't have the Q in the previous one because it is 1. So 1 times 1 is 1. So in this case, the order is for 300 milligrams of Pliocin. The drug on hand has a concentration of 150 milligrams per 2 milliliters. So our desired is 300, what we have is 150, and how it comes is 2 milliliters. So D over H times Q is the 300 divided by the 150 times the 2. 300 divided by 150 is 2, so 2 times 2 tells us we need 4 milliliters. Basically, this also will replicate a ratio and proportion calculation. Now, the ratio and proportion method is best used in sterile compounding scenarios that meet the following criteria. The drug stock is already in a liquid, injectable form, doesn't need to be reconstituted, and even if it does, once we're given the amount of reconstitution, we can use that concentration. The stock drug is in a powdered form, or the liquid or powder requires completion of additional steps. So this is one of the methods you should have learned in pharmacy math. It also was reviewed in the pre-course assessment. The left side of the equation is the concentration of the drug we have on hand. So always start with what you know on the left. That would be our concentration of the drug. So we use that as our setup. We want the right side to be what we need. So this is what we have. And this is what we want. So if we have milligrams on top, over here, we want milligrams on top over here. Now, this is like a balance beam. We have an equal sign. So whatever's on top on one side has to match on the other so that they're equal. So that tells us that if we have milliliters over here, then our answer will be in milliliters. So then we would go through this problem and doing our calculations and isolating x. X is equal to 1,500 milligrams times 10 mLs divided by 500 milligrams. Our milligrams cancel, leaving us with our milliliters. Get rid of a couple of zeros there. So I have 150 divided by 5, which makes 30 milliliters. So, ratio proportion. Now we have this one. Let's have you solve for the amount that we need. Okay, so now I'm going to walk you through it to check your answer. So first we're going to set up the ratio, and we're going to determine what we have that we are starting with. So this one is ciprofloxacin, 400 milligrams. A single dose vial contains 40 milliliters. So I have to read this information. So I have 400 milligrams and 40 milliliters. Then I have to decide, okay, now I know what I want. Oops, that should be milligrams. I need to see my order is for 200. Now you know that I'm only concerned with the drug. I don't want to worry about my base solution yet. All right, so I set up my ratio. Now I'm going to do my cross multiplication. So X is equal to 200 milligrams times 40 milliliters divided by 400 milligrams. Do my cancel, get rid of some zeros. So then I determine my division, and my resulting answer will be 20 milliliters. All right, how'd you do? The next method is dimensional analysis. So this is calculation by cancelization. I believe the majority of you practice this with Miss Ashante, and this is kind of your go-to. So that's all well and good. And like I said before, stick with what you know. So generally with this, we determine the answer first, so what we need, and we let that set up our problem. So because we're trying to find volume, generally what we're trying to find is milliliters. Determine the volume of the drug to prepare the product. You may need to do one or more conversions between different units of measure. Put the unknown quantity you want to define on the left side of the equation, and then follow by the equal sign. And start with the unit that you want to help set up that problem. So this takes you through the steps that you've already learned. So going back to that previous problem, if we need to know how many milliliters, and we want to do milliliters, and we go back to that Cipro label, 40 milliliters gives us 400 milligrams. That's our dosage strength, our concentration, and our order is for 200 milligrams. Now we cancel. So that gives us our 20 milliliters. Whichever way you prefer, stick with it. Now your flow rate calculations in the IV run or the batch, generally calculated on a 24-hour supply. Things we might need to determine include how long the bag's going to last, what time we need the next bag, how many bags we need for 24 hours. So we can use different ways to calculate those need-based calculations. So 3 methods for solving IV flow rate questions are best used in sterile compounding scenarios. The infusion rate in milliliters per hour is given on the CSP label. The total volume provided on the medication order or the CSP label, and the current time. So those are the items that we would need to find out how long will this bag last, or what time do we need the next bag. So to answer the 3 questions, when calculating IV flow rates, you have to know the total volume, the infusion rate, and the information can be found on the label. Drop factor relies on specific drop factor of the tubing. So how many drops per milliliter? Each of the different types of tubing will give a different drop factor. Macro tubing could be 10 drops per milliliter, 20 drops per milliliter, 15 drops per milliliter. Now a micro tubing, there's only one size, and that's 60 drops per milliliter. So that's an important one to remember, because that only comes one size. And then we use those drop factors to create the IV drip calculation. So, for example, this is what it would look like. The total volume in milliliters with the time in minutes, and then our drop factor in our milliliters. So if we're doing an IV that's a piggyback, generally it'll be infused over 15, 20, 35, 45, or 60 minutes. That one would give it as in minutes. If you're infusing a large volume parenteral, you may have to do an extra step in here to convert your milliliters per hour into minutes. The pharmacy also may use alligation calculations if we're mixing two different strengths of the same ingredient, or if we're doing a dilution. I know that you learn dilutions as a separate calculation, but dilutions can also be solved using an alligation, where your bottom concentration is 0 because you're using water or some other base that doesn't have any active ingredient in it. So you can review the alligation, and we'll go over this when the appropriate time comes. But this is just the process of alligation. The book does discuss it. You also did it in math, and I believe in pharmacy practice. So calculating skills, it's really important to have accurate calculation and measurement of the components that we're doing. We don't have a way to correct once a fluid solution has been administered to a patient. So if it's made improperly, it actually could cause a patient their life. So we really need to make sure that we're doing all our calculations properly. All right. So which one of these is the basic formula? All right, D over H is equal to X. Remember, that only works if your original concentration of the drug from stock is over 1 milliliter. An equation using drop factor is sometimes called what? If it's got drop factors, it's a drip rate. All right, very good. Some questions for you.